for this opportunity to share this conference with us.
Thank you very much for the introduction. I apologize, I have no Spanish, so hopefully the translation will help for those that need it. So, there we go. Okay, go the right direction. So, like I said, my name is Mark Fly. To get a background of kind of what I'm going to be talking about, I have spent the last 35 years or so running engineering departments for packaged rooftop manufacturers or air conditioning manufacturers. So I am certainly a little manufacturing centric and unitary equipment centric. But as part of that, being in that role and working a lot in HRI, the Air Conditioning, Heating, and Refrigeration Institute that regulates and certifies equipment throughout the world, and involved in ASHRAE. You know, I've been working on a lot of things here in the last few years, trying to push the envelope of where we got to go next, especially regarding equipment efficiency. So you've seen a lot today about decarbonization and energy efficiency and how we can get farther. The best way to save energy is not to use it in the first place. So, you know, first thing you do is you do your energy conservation measures in your building, good insulation, well-built buildings. The second thing you do is you put the most efficient equipment you can put on that piece of building. And so we have to talk about how do we decide what's most efficient. And that's really what I'm going to be talking about. Now, this is an ASHRAE DL. ASHRAE asked me to put a couple of slides up there. The DL program is set up with some co-funding from ASHRAE, typically co-funding from the chapter to bring people in from all over the world. Fortunately for me, I do a lot of these because my ex-company that I retired from last July continues to pay my way to go out to these and talk. So I'm very popular because I'm very cheap. So I do a lot of these talks. But if you're not involved with the local Monterey chapter, which by the way, in my opinion, is the best chapter in ASHRAE, and I've seen a lot of them. You guys are amazing. The enthusiasm and the drive here is incredible. If you're not involved, get involved. I went to my first society meeting in 1986. There are 2 society meetings, a summer and a winter meeting every year. I have not missed a meeting since 1986. I have been on the board of directors. I'm currently on technology council. I've on the ASHRAE Foundation. I've done a lot of things. I put a lot of time into ASHRAE. I can guarantee you that I got more back than I ever put in. And what you get back is the people you meet in meetings like this, and the people you meet sitting on these committees and working on these. I can call up my most rabid competitor and ask him a technical question, as long as I'm not talking about pricing and markets and some other things, and we can have a conversation. So it's invaluable to your career. So if you're not involved, get involved. It is very important. So there's my advertisement for ASHRAE. So we're going to talk about the differences between equipment and system efficiency. And I'm going to introduce the concept of what we call max tech. We're troubled in the efficiency world by Newton's second law of thermodynamics. We can't make a net zero piece of equipment. You know, we're not going to be able to produce more cooling energy than it takes to generate it. It's a law, it's not a suggestion. It's Newton's second law, it really works. So to get better in efficiency, we need to really look at how that equipment operates and how we use those in buildings. And we're not there yet. So the young people in the crowd, or the people that are beginning their career or still have a long ways to go in their career, there are tons of opportunities for you going forward. Everything is not known about everything in air conditioning, not by a long shot. There's tons huge amount of things to do in the future. So let's talk a little bit about system efficiency. if you're going to talk about system efficiency, everybody has to show this slide. You know, it's about 44% of a commercial building is consumed by the air conditioning and heating systems. This slide's a little dated. In a very modern building that you build today, the lighting load would have went down. The plug load, because of all the computers and server rooms that we have in that building, went up. It's about the same. It's still about somewhere between 40 and 45% of the energy is consumed by the air conditioning system. So we want to put the best air conditioning system we can in there. And so what's evolved over time is, you know, what's the best system? Well, it's kind of everybody's opinion, right? But so we came up with these metrics and we came up with these regulations, and especially in the United States, we are highly regulated in the commercial environment. And the problem with regulations is that, you know, they're words written on a page by a bunch of lawyers, and what happens is people find ways around it. So we don't design equipment today. As a manufacturer, I'll tell you the dirty little secret. We don't design equipment today to be the best piece of equipment for your building. We design equipment to give us the best number that we can go sell it by. And so that is not always exactly the same. So, you know, regulations are a necessary evil. People want some way to simplify this, but it's not a simple problem. So I'm going to go through some of the history of 90.1. So the ASHRAE energy standard across the board, minimum efficiency is 90.1, started in 1975. So we had the 90.1 standard, and here's the progression down with the red dots kind of being some future predictions that the 90.1 committee's put together. If we look at a typical 3-ton residential, small commercial office building or small commercial store type air conditioner, and look at how it progressed, percentage of efficiency for what was the standard in 1975 till today, you'll see that in the 1980s and 90s, late 80s and 90s, man, we did a lot on efficiency. That's not because we learned all kinds of new wonderful things during that time period. It's because in 1975, that equipment was really, really bad. It was really, really inefficient. It was the cheapest thing that we could do to make cold air coming out of the diffuser. So it was not good equipment. But you will notice that as time has progressed, the slope of that line is not following the slope of the line of the 90.1 standard. If we look at a 10-ton rooftop unit, a little bit bigger unit, it wasn't as big a jump in the 80s and 90s because these were commercial buildings from people who were trying to make a profit on their business, so they paid a little bit more attention to what the efficiency was. The equipment wasn't as bad in 1975, but it's kind of progressed a little closer, but it is also beginning to flatten out. Now, if we look at air-cooled chillers and overlay that with a water-cooled chiller, you'll see that those lines have really flattened out over time. And so what's happening is we're approaching what we call max tech. So one of the ways to get your air conditioning to be more efficient, you have a evaporator side, which provides the cooling to the space, whether it be water or air, and you have a condenser side, which rejects that heat or cool, if you have a heat pump, out to the outdoor air. And the way you make it more efficient is you put more of it. You put more copper, you put more surface area in the chiller, you put more surface area on the evaporator side, the condenser side, and we're reaching the point of diminishing returns. The best-in-class water-cooled chillers today are approaching 1 degree approach on the condenser and 1 degree approach on the condenser. 1 degree approach on the evaporator, 1 degree approach on the condenser, 1 degree C, roughly. So what that means is that the refrigerant saturated temperature is within 1 degree C of the water that's leaving that chiller. And the refrigerant condensing temperature is within 1 degree C of what's coming off that cooling tower. So if we want to make that a 0.5 degree C, we may have to put 100 times more copper in there, and we're going to change the efficiency of that machine a few fractions of a percent. So at some point, Newton's second law takes over. We can only make so much. You have to have a delta T to move heat and cool across the surface. So we're going to get there. We are virtually there on the best-in-class chillers. We kind of know what to do there. There are some other things that we can do, the minor effects, better compressors, better control, but the brute force of actually the refrigeration cycle, we're getting very close. Rooftop units has got a ways to go, but I think somewhere around 2039, somewhere around in that range, we'll probably be at the same spot on rooftops. So, my clicker has stopped. Try again. There we go. So if we kind of look at this, here again, this is the projection. The bottom green line is, we're going to make net zero pieces of equipment. Well, that's not going to happen. There are other projections kind of looking at the slope of the curve, but really we're not going to get there. So how do we save energy? I think we have in general, pretty good equipment today to work with. What we don't typically do a very good job is apply those and operate those buildings properly. And you've heard a lot of that. Like I said, I have no Spanish, so I've been looking at the slides and gathering tidbits of the presentations. You've heard people talking about optimized control systems. All those things help this, but it's not the equipment. So it's not going to change the IPLV, the IER, the SEER of that equipment. It's operating it properly, so that's very important, and it's very much dependent on your building and where you are in the world. So this is a chart that I borrowed from ASHRAE Standard 90.1 Committee, and they've done hundreds of these for different type buildings. This happens to be a hospital in Zone 4A, that yellow band. That yellow band is Atlanta, Georgia, and Washington, D.C. happen to be in that. That yellow band, their design summer temperature is 95 degrees F, about 35 degrees C. So strangely enough, that's where we test all the equipment at, Washington, D.C. and Atlanta, Georgia, home of ASHRAE, home of the U.S. government. So all those ratings are kind of set there. And so if you plot a chiller IPLV on there, the blue dots are the cooling actual load that building needs. The red dots are the heating load it needs throughout with different ambient temperatures going across the bottom. So if we go up here to the very top here, that's the full load efficiency. Notice there's no operating hours there. So in general, there are just, if you design your building and you do your heat load according to ASHRAE and you design to 1% or 0.5% weather data, that means only 1% or 0.5% of the time will it be there. And then every engineer likes to be a little conservative because you don't want to be the guy that shorts the people on their air conditioning and get the call that I'm hot today or I'm cold today. So the engineer adds a little safety factor. ASHRAE actually load calculations I always felt like it did 10 to 15% safety factor just by the way it worked. And then you round up to the next biggest piece of equipment because you don't want to short anybody out. And so you never operate at 100%. Now, if you look at IPLV or NPLV on chillers, IPLV for bigger direct refrigeration equipment, SEER for other equipment, the point that makes the most difference is the 75% point right about there. So that is the point that makes that number the best. So as a manufacturer, I really try to make equipment that works really good at 75% because I want that number, because when you compare me to my competitor, I want a more efficient number there so you'll buy my piece of equipment, right? That's just human nature. We don't design that piece of equipment to operate here, which is more the average point where that actually runs. And none of them really run down. That line isn't going through here. So there is some opportunity, if we were looking at this differently, which I'm going to talk about how we do that, to optimize a piece of equipment where it would run best where you run your building the best. That's really not what we're doing today, because we've got these artificial. And if I did this for SEER, if I did this for IPLV, if I did this for different climate zones, all the charts kind of look the same. You know, they're always out there. And, you know, here in Monterey, you're not in zone 3A. You're much hotter, probably, most of the year. You're closer to where I am in Tulsa, Oklahoma, in that orange or red line, where you're, and plus you have way more hours in the cooling side, less hours in the heating side. So, you know, today we've been looking at this product performance, this big, bold thing, and we've moved a few places, because when I first started in the industry, we only looked at that 100% load. We looked at the EER. That's all we cared about. But now we've moved up and we've got some part load efficiencies, but we really need to get up and understand what are the energy needs of the building and how is it used, and then how do we make that system most efficient for that building. And so this is a chart that came out of, there again, 90.1, where they're doing a lot of study on this. That committee meets, I think they have a weekly conference call. So if you've tried to keep up with ASHRAE 90.1, you know, they go up to, you know, addenda ZZ, and then they finally publish a new one. They start at addenda A again and do it again. So it's always changing. But right now we're kind of in this orange box. We have, SEER has some regional codes for regulations. There's a hot, dry, hot, humid, cold environment. So there's some differences in just the very lowest tonnage residential equipment. Most all of the equipment now has part load efficiencies. Water source heat pumps are working on them. VRFs are working on them. So there's some systems that haven't quite got there yet, but they're getting close. To have some part load efficiencies where you can kind of look at that and have something like a SEER and IPLV, which is better than the old EER one, but not good enough. So, and so today I've got a couple examples. So if I look at a rooftop unit or a piece of package refrigeration, what's in the red box is what determines the rating on that piece of equipment. If you look at the SEER or IPLV, we have an evaporator coil, we have a fan. The fan is running at a very, very low static pressure during the testing condition, not realistic, by the way. So there's some work that needs to be done there. We look at the condensing system at that 195-degree point, or the points on that part load. We have a filter that's about a MERV 5 filter. It's 0.15 inches of static pressure drop for you filter people out there, not much. And And if you don't want to put a filter in it, you just take the 0.15 default. So nobody ever puts a filter in one, because that's as low as any filter ever is, usually. So, but we don't pay any attention to how we handle outside air. We don't have economizer cycles. We don't look at the ductwork. We don't look at VAV boxes. We don't look at the building. And we don't look at the community and how the energy gets there. So there's a lot of different levels we can start stepping out and doing a better job with. Chiller is a little bit worse. On a water-cooled chiller, we look at the water at only the chiller, the compressor and the two surfaces inside. We have a fixed water coming in, a fixed water going out. We don't look at the pumps, the cooling tower, the air handler, economizer, VAV boxes, the rest of the building, or the community that's serving it. So we have these ratings on these small components, but they're not system ratings. And where we really need to get to is looking at a more holistic approach to how the system works. And so to do that, we need to do building energy modeling. How many people, anybody in this room do building energy modeling as part of their job? There's one, back in the back. So, you know, building energy modeling is becoming more and more important because to understand how the buildings use the energy, and to kind of predict how it's going to work, we need to do that. And to do that, we need some good input data. I'll talk about that here in a minute. So This is kind of the history of building energy modeling back from the 1970s. So in the 1970s, the U.S. Department of the Army and the U.S. Air Force got together and they developed a program called BLAST. And a good friend of mine, Dave Kniebel, worked on BLAST. And there's a few old guys still alive that still worked on that. So this was mainframe, punch card, punch tape, early day computer stuff. And it was really good for 1970, you know. But they developed this program, and that was kind of up here at the top. All these little bar charts, this eye chart that you can't really read, all these little things going down there is the evolution since there. And really where we've got to in today, there's a program called Energy Plus. And most of the energy estimate programs, and there's a bunch of them out there, but most of them go back, they have a core that's Energy Plus. That's kind of the accepted methodology to calculate energy in the building. The problem with Energy Plus is it's still using the equipment models out of BLAST from 1970. And those equipment models are really, really bad. You kind of put in what's the full load efficiency. It has a canned efficiency curve in it. It's a straight line, which it really isn't in reality. Nothing's a straight line in the real world. and they're just bad. So if I go into a room and if half of you were doing energy modeling, I'd say, how many of you, when you do an energy model and then a year later you compare the utility bills to how your energy model said that building would have operated, do they agree? And everybody drops their hands, right? Because the agreement, the validation on those isn't very good. Unless you do one particular type of building. Data centers. Data centers are very easy to predict. If you have 500 watts a square foot load in the building, what happens outside doesn't matter anymore, and it's a constant load. Those things run all the time. So they're pretty good at predicting. That's because they have no variation, and they're basically running very close to 100%, where that BLAST model is pretty good. So there was a relatively new ASHRAE committee, ASHRAE 205. And if you remember anything else out of here, you need to understand that 205 exists. And they published this late 2023, the first standard. And 205, the goal of 205 is to create equipment efficiency maps. And if you're going to do that, it's kind of like BACnet came out for controls. It was, you need a standardized form. We need a way that all the manufacturers can put something in a standardized form and tell the consulting and contracting and building owner community how this equipment's going to work. So, like I said, for 35 years almost, I have run some kind of engineering department for some kind of manufacturer. Actually, there's just two of them, but and so I was all the time getting people to call me up and say, hey, could you give me a part load efficiency of your piece of equipment? Give me 10%, 20%, up to 100% efficiency load on the building. Tell me what the part load is. My first question is, okay, what indoor and outdoor temperature would you like me to give those to you at? All of them. Well, I can't really do that. So that's a lot of work. And so what really 205 is all of them. Now, in the US, I said HVAC equipment's heavily regulated. It's regulated off of a law that was passed in 1975 by same year that 90.1 was created, called EPCA, or the Energy Policy Act. And EPCA had in it a list of products that the government could regulate. Incandescent light bulbs was on that list. So in the US, you can't buy an incandescent light bulb anymore. You have to use LED or fluorescent. Washing machines, refrigerators, everything was on that list. All the HVAC products, they left one off. Anybody know what that was? Chillers. They left water chillers off the list. The only HVAC product that is not heavily regulated by the US government in the US is water chillers. You can sell somebody a IPOV6 chiller if they're willing to buy it. You could sell them a terrible chiller if they're willing to buy it. It's not against the law. It's not a good idea, but it's not against the law. So Strangely enough, the only product that's ready for 205 is chillers. Because if you have an HRI certified chiller, you're not certifying the IPLV anymore. This happened several years ago. So if you go and get your chiller certified, what you certify is your computer selection program. And if your computer selection program says that that chiller will run at a really silly position, freezing outside with 25 degrees C water coming out of it, and 60 degrees C water coming in, whatever stupid condition you might happen to have, and your program will give you a number, that number is certified. And so when they do testing to make sure that you're not lying to the public and do testing on that chiller, they test at the IPLV points, the 4 points that normally we've tested forever on at 95 at the high end, and somewhere in the 50s at the low end. And then they test a random point. And what HRI will do is they'll go around, take your program and try to find find the edge of where it will select something. They'll test you at that point. If you fail that point by, say, 20% in efficiency, you have to derate your efficiency on every point in your selection program by 20%. So this has got some real teeth to it. So water chillers and the water chilling community that have certified chillers have spent a lot more time testing their equipment and understanding where they run at all these oddball conditions, or even something other than the IPLV conditions. As a rooftop unit manufacturer, I can tell you all kinds of things about all my equipment at 4 data points. That's all I know. Because I need 4 data points to calculate SEER, IPLV, or SEER or EER, and IER, and so that's all I really need. And because no one's asking for it, nobody does it. If there were a bunch of energy modelers in here, the next question I would have asked was, how many people do an energy model when you don't get paid for it? And the hands all go down again. If you're not paying the manufacturers to get 205 data, you don't get 205 data. So this is in the world of air conditioning, this is a very recent standard. It hasn't really caught hold. We're still arguing in the manufacturing of packaged equipment in particular about how to do this, but now we have a structure and we're going to get there. So if you're working for a manufacturer, maybe you can get involved in doing some of this. We need better computer models. The thing about chillers is they're relatively easy to model with water because, it's, in English units, it's 500 times the GPM times the delta T gives you the capacity. You don't have latent load. Latent load is very hard to calculate on an evaporator coil, or latent load on a air handler is very hard to calculate reliably. So it's way more complicated math. So we really don't have models for that, but we're getting there. Most manufacturers have some kind of model, but they haven't done the testing to know that it's good all the way around the envelope, and that will have to happen. And so, like I said, the 205 committee is looking at all kinds of expanding their range and working on these data tables and trying to get these better. So, in conjunction with this, HRI, if you sit on HRI committees or ASHRAE committees, about half the people in the room are familiar faces. They work on both. I always say, when I talk to students, I always say there's only 24 people in the HVAC industry who all know each other. It's really a small industry, but there's a committee in HRI called the System Steering Committee, and their goal is to figure out how to do system efficiency versus unit efficiency. How do we better describe our equipment to our customers so that they can evaluate? Because I might have 2 pieces of equipment with the same IEER, and if I put it on a certain building in Monterey at your climate conditions, one may use less energy than the other just because it happens to operate better at the condition you run most in, or the set of conditions that you run most in. So having that single number, all of a sudden you have to run an energy model to tell whose body's equipment's better. But I don't think that's a bad thing. It's going to give you a better answer. The other thing that happens in 90.1, in all these building models, is the control systems in those building models are very simplistic. So they don't really do a good job of figuring out how controls really interact. And there's lots of things that can happen in control systems. So the other thing that the people that are working on Energy Plus and all the energy modeling programs are trying to figure out is how do we put standardized sequences of controls. So ASHRAE has developed through other standards, standardized sequences of controls. How does a VAV system really work? How does a constant air system really work? How does a dedicated outdoor air system work? And how do you get these controls kind of in there where they simulate that throughout the day so you get a better answer out of the building modeling program? The other thing is we can't just look at the building. Now, if you talk to utility people about energy efficiency, they could care less about the part load efficiency or anything else. They want to know what the EER at full load is. Because from a utility standpoint, on the worst day and the biggest drought, on the hottest day of the year in Monterey, California, how many amps do I have to put out of my power plant? And do I have enough power plants to do that? And if I don't have enough power plants to do that, I have to build a new power plant that's going to sit empty and do nothing most of the time. So they would like us all to run like data centers where they knew exactly what the load's going to be and it's constant all year long, and they make their most profit doing that. So that's when that equipment's the most efficient. So we have to look at this. And so there's many things. Thermal storage, which was a big thing in the 80s, is beginning to come back into the industry because we need some way to store energy. And if we're going to rely on solar and wind and those kind of technologies to help provide our electricity in a greener world, those aren't constant sources. The wind might not be blowing and the sun may not be shining that day, and it's certainly not shining at night. And so, especially in the heating load, the coldest day of the year, it's cloudy and the wind's still, typically. So how do we store energy? And one of the ways we could do that is with thermal storage of ice and water. Those things help that utility company by leveling that load out. So we've started seeing things in certain parts of the world where they talk about smart grid. So a smart grid system works like this. If you have air conditioning in your house or apartment and you've gone to work that day and it's noon and no one's in the house, the smart grid would say, hey, all the industry in that town is really cranking up and they're using a lot of energy. We need to be able to provide more energy. Could we go back and raise the thermostat setting at all those residences up 5 degrees, 10 degrees for a little while so that I can provide energy to the businesses, and then when the businesses start closing down and everybody gets on the road and gridlock traffic in Monterey at 6 o'clock at night and takes them an hour to get home, during that hour we can be cooling your house back down so when you get back home it's okay. But to do that you have to be, the utility company has to talk to your air conditioner, and that's what smart grid's about. So that's a future technology that I think you'll see coming up. So, if you're in this, if you've got a consulting business or in business, obviously we're all in some kind of HVAC business, the things that I think are really going to be the winners in innovation and the people that will win will the people that understand how these dynamic models work, how do we get good 205 data, and how do we provide feedback into that system. And before we can go off and talk to regulators or talk to anybody about how to do this, we have to learn how to do it. Today, Energy Plus cannot read a 205 data and give you a number. They're working on it, but so we have a standard, we have a set of data that we can get out, but we have no way to use it at the moment because this is all bleeding edge technology, but we'll be there in the next few years. So the other thing, and apparently I hid that slide unintentionally. The other thing that I think is very, very important on buildings is commissioning. So you have designers that go out and design the building. They do the best job they can. Sometimes they're good, sometimes they're bad, but they had a plan, right? 2 years, 5 years, 10 years after that building's built, is it still operating to that plan? That's the question. So continuous commissioning, keeping track of that. My classic example is, say we've got 200 people in this room, and it's getting really hot in here because the air conditioning system can't do it, and they call the maintenance people up and they say, I need more air conditioning, or I need more heat if it's the middle of the winter time. And what do the maintenance people do? They're firemen. They're putting the fire out that day. They're not thinking about energy efficiency or anything else. They want the people in the room to get off their back. So they go out and they take the actuator off the outside air damper and shut it down. They do whatever they have to do. Next day, do they go back and hook that back up? No, they're on to another fire. So buildings over time get operated worse and worse as they get older in many cases, or people turn off the circulating pumps on the hotel, so their hot water takes 30 minutes to get hot water up to the 14th floor of the hotel. So what do people do staying in that hotel? They turn the shower on 30 minutes before they want to take a shower. Did that save any energy? Or water? No, not really. But that's the mentality, because people are being driven by things that are different. So I think there's lots of opportunities to move forward. I think you'll begin to see more intelligent listing systems and more intelligent ways to rate equipment. And so if you're in the business and you're looking at what you're going to have to do in the next 5 or 10 years, look at building modeling, look at controls, and look at commissioning. Those are the three things that I think will really make a difference in how much carbon we put in the environment out of a building, once we've done all the other things that we need to do to keep carbon out of the environment. So with that, I would be glad to answer any questions. And if it's in Spanish, I've been promised I can hear them through this. Because we have a nice young lady back there that's figure out how to get this in my ear. Yes, I can hear you.
En los proyectos que ha participado, ¿qué tan frecuente es que le soliciten el modelado energético?
Not often enough, actually, and it's very dependent on the building, and the owner. So, and I saw some slides up here talking. I saw ESG gets flashed up there. So big corporations, some of the bigger, probably U.S. companies that are coming down here, they care a lot about carbon and energy efficiency, and so they're more likely to do energy modeling than people that don't, that are just building the local grocery store or local retail store in it. So it's really today the high project. I always call them ego projects, the people where they want to be able to say they're the best company in the world because they are the greenest or the most carbon free. They all make these pledges. I'm going to be carbon free in 2030 or 2050. Those companies are doing a lot of energy modeling. The average, so for a consulting engineer in the U.S. That's working on buildings, I'd be surprised if it was 10% of them get modeled in general. But it's moving up. There are more and more every day.
Cuando los proyectos se ejecutan y se ponen en servicio, ¿qué práctica regular o cuál es la solución que se tiene para hacer seguimiento al desempeño energético de edificios y de sistemas de aire acondicionado?
So there are some things that are happening around the world, and people trying to get that more regulated. In Washington, D.C., they have a recent law, if it hadn't been redone, because we have a new administration in the United States, in case you haven't noticed. So some things are getting reversed. But in Washington, D.C., they were measuring every building's utility energy use, and they would set what they call an EUI, which is BTUs per square foot per year that building used. And if you went backwards on that for so many years, you got fined so many dollars a square foot that year. You paid extra tax, basically, on that building. So there are some people who are really trying to enforce that. There again, those people that are in these big corporations that are looking at I want to be carbon neutral or carbon free in some year, they plot on a graph and put on their website every year how far they got down. So if they're not moving in the right direction, then they're going to pay a lot of attention to it. And they're the most likely people to have this continuous commissioning. So if you're an engineer or a contractor and you have that skill, that's a steady paycheck. You're going to be in buildings every year and looking at them and making sure that they're doing what they're supposed to be doing. Because I know what I always used to say, I kind of started out life as an energy auditor back in the 80s and or early 80s. And a lot of times it's not the low-hanging fruit, it's the fruit that you're tripping over on the ground. It's pretty easy to go into a building and find all the big energy wasters if you just look. And there's usually a lot of them if nobody's paying attention. So I think there's a movement in certain areas to do that. You know, certainly in Europe, more so, or you know, Eastern Europe especially, more so than in the United States. Certainly in the U.S. on the coast, but you know, as you in Mexico probably realize, you know, everything kind of starts on the. A lot of times it starts in Europe, it moves to the coast of the United States, it filters on down to the center of the United States, probably funnels on down into Mexico at some point. So you know, we're not all the most, certainly Tulsa, Oklahoma is not the most progressive state in the world in doing that from a legislative standpoint. From my personal standpoint, I'd rather not be told by the government what to do. I'd rather start looking at the economics. But there's money to be saved, and not only does it feel good not to use carbon or not to use energy, it also saves you money, makes your business more profitable. So I think there's some things that do that, but there isn't as much of that needs to be doing, kind of like there's not enough energy modeling that needs to be doing. So. No one else? Okay.
Haga el micrófono porque luego no escucha el traductor.
En las diferentes presentaciones se ha mencionado continuamente lo de Net Zero 2030. ¿Esto es realmente demasiado ambicioso? ¿Es realmente se puede alcanzar? ¿O es simplemente una meta que está ahí y ver qué se puede lograr?
Well, okay. I'll tell you my own personal opinion. If you listen to my bio, and I think you probably read all the bio, I had a physics degree when I went to school. So, you know, second law of thermodynamics is very close to me. So a lot of people say net zero energy. That really bothers me because that's not possible. So that's the 100% efficient perpetual motion machine. Net zero carbon is completely different. Right. That's net zero is to generate as much as you use over time, which means we also need to learn how to store things. So part of that, are we going to get to net zero? How good are we going to get at storage? Today, a lot of the storage is in batteries. There's some new things coming in batteries that are helping a lot. The batteries we have commercially today, not so good. Plus, they're very expensive, and their carbon footprint, what it takes to make that battery, is very not environmentally friendly. So can we get there by 2030? I think 2050 is probably a more realistic goal, but you always have to have a goal, and things will change over time. You know, we'll change our thinking, we'll look at different things. We probably won't keep the same, even if we're going in the same direction, we won't keep exactly the same focus through that. We'll redefine how that actually works. But, you know, I think you need a goal because you need something to shoot for. You need to know that you're going in the right direction. So I think it's a very admirable, lofty goal. But to make that work, to make that net zero work, you have to figure out how to level that load where you can provide all that with hopefully renewable resources, hydro, geothermal, wind, solar, whatever else we can come up with that's very sustainable. Okay. All right. Sure.
¿Me apoyas, por favor? Yeah, so Mark, we are very glad that you are here, and in the name of the chapter, Monterrey chapter, we can give you this this present for you, and thanks to be here in this sixth regional conference in Monterrey. Yeah, gracias por estar aquí, Mark. Sí, bueno, señores, pues primeramente quiero agradecer primeramente a todos ustedes que hicieron posible este evento de estar aquí. También, muy importante, gracias a todas las personas del grupo de ASHRAE. ¿Dónde están? La gente de ASHRAE, Monterrey, por ahí. Todos gracias por participar, porque tras bambalinas hay muchas personas que colaboraron. Está nuestra próxima presidenta electa, Paula. Está Peter también en redes, Janet, Jackie, Ricardo Arellano, Donald Hay y todos los que hicieron posible esto. Brenda, gracias Brenda. Y pues bueno, por último nada más quisiera también darles unos pequeños avisos. Invitarlos a nuestra próxima sesión técnica, que va a ser el día 20 de marzo. Recuerden que nosotros sesionamos cada segundo jueves de mes. Esta ocasión lo vamos a brincar una semana más, entonces va a ser el día 20 de marzo, va a ser una plática muy interactiva, muy dinámica, se van a divertir y van a aprender mucho. Entonces los invitamos cordialmente a esta conferencia para que hagan sus anotaciones ahí en su agenda, ¿ok? Y bueno, no olvidarnos tampoco que vamos a llevar a cabo la segunda edición de la carrera corriendo por un aire limpio, que es la Huella Verde, Descarbonizando Nuevo León 2025. Va a ser el día 13 de abril del 2025, el día 13 es domingo, entonces hay que levantarse temprano para estar a tiempo. 7:30 de la mañana tendremos las categorías de 10K, 5K, y 1K. Es una carrera para convivir también y aprovechar con la familia. Podemos correr desde niños, adolescentes, adultos, etc. Va a haber grandes premios también. Tiene un costo muy económico, muy accesible para todos los miembros y pues bueno, incluye todo el kit que es su playera, medalla, un bote de hidratación y algo más por ahí. Entonces ahí está el código QR por el cual se pueden inscribir y pues los invitamos a participar porque estamos buscando y apoyando las iniciativas de un aire limpio en Nuevo León y esta es una manera de contribuir a esa participación. Y pues bueno, ¿algo más, Paula? ¿No? Bueno, pues por mi parte me tocó, bueno, ya está el boletín también, el boletín mensual, ya está por ahí en las redes sociales para que pueden enterarse de cuáles son las actividades que hemos realizado durante el mes que pasó. Y si quieren revisar boletines anteriores, ahí están en la página, los pueden ver. Bueno, señores, pues por mi parte es todo por parte del capítulo Monterrey. Paula, si quieres pasar, Janet, sí. Les agradecemos de todo corazón el haber participado. Que me siento muy solo aquí. Les agradecemos de todo corazón haber participado. Paula, ¿algunas palabras?
Pues no, muchas gracias a los patrocinadores, en específico Belimo y Honeywell, y pues agradeciendo su presencia a ustedes también. Una mañana pues muy interactiva y de aprendizaje, y los esperamos pues en los próximos eventos.
Bueno, para que no, perdón, mejor no lo dije, Paula va a ser nuestra próxima presidente de ASRE el próximo año. Entonces, gracias.
Y bueno, los invitamos a la carrera. Tenemos un Instagram, huella verde_ASHRAE, y el 100% de lo que se va a recaudar es para a nivel sociedad, para poder diseñar y tener equipos sustentables. Entonces, el 100% es una carrera a beneficio. Los invito a participar. Gracias.
Gracias a todos. Gracias y buenas tardes.